I will go back to some of them, but retry installation. I don't know what is going on. So now you can see and you can.
Yes, that's okay. Yes,
it's okay. Okay. So let's start from the following more or less understandable construction. So we want to define a Poisson bracket between traces of some matrix polynomials. It follows from the state of the problem that because the product of traces is not trace of something, that we want to get a Poisson brackets on a vector space, not on any algebra. So we cannot speak about Leibniz rule. It's more or less typical, for example, in the situation with PDEs and so on, but let's fix this fact. So we have several matrices, and we want to define the Poisson brackets between traces of matrix polynomials, non-commutative matrix polynomials with a constant coefficient. So the most naive version is the following. We consider all entries of this matrix, x, I, j, alpha. They are entries of our matrices, and we consider them as the coordinates. First of all, I need to stress that I assume that all these elements are functionally independent. This means that the size of matrices much greater than the number of matrices. Otherwise, you know, if n is small, then there are some polynomial relations between matrices. And I assume that we have known these polynomial relations, and all these guys are functionally independent. They are coordinates of our polynomial generators of our polynomial rings. And what we want from this Poisson brackets. First of all, it has to be GLM invariant. And second, our main goal, the Poisson brackets between any traces is a trace of some polynomial. That's all what we want to postulate. And it's not difficult to find the ansatz for such brackets. It's strange. This is a remark. Suppose I have such a bracket, and if I have H as a Hamiltonian trace of some P, then it's easy to verify that the equation of motions can be written in the matrix form. Not, of course, we can write this in the entries of matrices, but we can combine them to a matrix differential systems where F, alpha are non-commutative matrix polynomials. Now let's look how such brackets can be written. The first remark, if our two assumptions fulfilled, then the linear brackets, linear means that, no, not linear, constant, constant brackets is given by any set of skew-symmetric constants C alpha beta. And this is a general form for constant trace Poisson brackets. Trace means that our two assumptions fulfilled. And for linear brackets, this is the main ansatz. If the brackets satisfy to our assumptions, it has the following form, but not for arbitrary sets of constants. And the quadratic brackets is given by such formula. What I can say about this ansatz? Look, in my approach, alpha, beta, and gamma numerate the matrices, and I, J, I prime, J prime is related to the position of the entries. And the position is more or less here, and the constant depends only on the matrices. And now about algebraic relations for constants. We remember that for usual linear brackets, the set of constants are structured constants of Lie algebra. Here, so it's the first trivial remark. For the constant trace Poisson brackets, we need only skew symmetricity. But for brackets number 3, we get immediately this identity. This means that B, alpha, beta, gamma are structure constants of an associative algebra. Not Lie, but associative. It's much more rigid situation than in the usual Poisson brackets, linear Poisson brackets. And now the set of conditions for two tensors. Here we have two tensors, R and A. And the interesting set of brackets corresponds to the case when the tensor A is identically 0. So without these terms, it's also interesting, maybe the most interesting situation. But in general, you have two tensors. And let's look to the relations. Two relations are just for the tensor R without A. And this means exactly that these tensors satisfy to associative Young-Baxter equation. So we have a set of such trace brackets without A, where this is an arbitrary solution of constant associative Young-Baxter equation without parameters. The first remark. And as for tensor A, we have one relation between them and two relations for A and R. I can rewrite all this identity in the tensor form, but for me, the meaning of these identities are not completely clear. But this is a good start.
Volodya, may I ask a
Yeah.
question?
Yeah.
So why you assume that you have a sort of trivial algebra inside the metric structures? So basically, so all non-triviality, and when we consider relations between different matrices, like this, yeah, the delta functions or whatever. So
I would say for simplicity, if I
no,
have
it's just a question. It's an ansatz or it's a theorem. That's the only question. So if it's your choice, then it's fine.
no, if the elements of matrices are independent, then this is the statement theorem. Any trace brackets under this assumption, no algebraic relations between matrices, are given by these formulas.
Okay. No.
That means, Volodya, that for instance, if you want to work on free algebra and use a matrix representation of this free algebra, right?
Yeah, exactly. But let me finish with the matrix representation, and after that I will try to define the Poisson brackets on a free associative algebra. Yes, it will be a representation for any n capital. Now, the remarks are evident. B alpha, beta, gamma structure constant of any associative algebra if and only if. And you have standard Lee-Kirillov constant interpretation of these brackets. This related to the algebra of matrices with entrances from A. Okay, now I want to discuss a little bit the situation when A is identically 0 and we have pure associative Young-Baxter equation. There is a nice algebraic interpretation of these brackets, and I want to give this relation between such brackets and so-called anti-Frobenius algebras. Why Frobenius, why anti, how it related to Dubrovin and other situations? No relations. Anti means that our non-degenerate bilinear form is antisymmetric, skew-symmetric, not symmetric. So we have, by definition, a bilinear form, skew-symmetric, non-degenerate, and non-degenerate is the most non-trivial condition here on our associative algebra. Or if you want, this form defines one cocycle. So this is identity for our antisymmetric bilinear form. And what's clear that if the algebra has a unity, unity is in the kernel of the form. So semi-simple algebras, they cannot be anti-Frobenius algebra. There are different interesting classes of examples, but again, the condition of non-degeneracy is very strong, and it's unclear how to describe such algebras. For example, I would say this is the first algebraic problem to describe all anti Frobenius algebras of this form. This is a semi-simple associative algebra, direct sum of matrices, and this is bimodal with trivial multiplication. There are many such examples. This class is interesting and non-trivial from the point of view of application, but I know the description only is a dimension, I don't remember, 2, 3.
Volodya, may I ask you a question?
Yeah.
When you talk about your anti-Frobenius algebra, your form take values where?
In constants?
In the field?
Да, the constants field.
Okay.
Okay, and the statement is, I am not sure who was first, who formulated the statement in this way. I don't know really. We found this statement ourselves, but probably before it was known in a different form, maybe. So there is one-to-one correspondence between our quadratic brackets without a equal to 0, or solutions, or if you want, solutions of associative Young-Baxter equation up to equivalence. Equivalence means that we have a conjugation of all matrices by one matrix, and representations of anti-Frobenius algebras up to isomorphisms. So if you want to construct the constant solution of associative Young-Baxter equation, instead you can construct some representation of anti-Frobenius algebras. And I want to show the construction to one side. Suppose we know an n-dimensional representation of anti-Frobenius algebra A, then they matrices define the representation. This is the matrices of our matrices. We have our skew-symmetric form, and suppose the matrix of this skew-symmetric form is G alpha beta, and this is the matrices of the inverse matrix. Then it turns out that this formula gives me a solution of the associative Young-Baxter equation. So this is the matrix inverse to the matrix of bilinear form, skew-symmetric, and they are matrices of the representation matrices. So for me, it's an interesting statement, but okay. But now let's try to define the non-Abelian Poisson brackets on free associative algebras. Probably we can consider not only free associative algebras, but algebras with constraints, but I'm not expert in this story. Maybe we can ask Sasha Mikhailov how to find the quotient algebra such that Poisson brackets becomes to be Poisson brackets. Okay, but now what we can say about the trivial idea. The trivial idea is just repeat the definition in the commutative case. In the commutative case, you have a commutative associative algebra. You simply ask for the Leibniz rule and for Jacobi identity. But it turns out that if you try to do the same in the non-commutative case, the set of real examples more or less are just simply commutators in algebras, no more. It's very poor idea and no examples if you want to define the Poisson brackets in the usual way. But instead, we are going to, in some sense, follow to Maxim Kontsevich. He developed this approach for non-commutative symplectic algebras, not for general Poisson brackets, polynomial, quadratic, just symplectic. But the main ideas can be found in this paper in 1993. We have some paper with Sasha Mikhailov. This paper was related to integrable ODE on associative algebras, but we propose the definition, one of possible definition of such algebras, not only symplectic, but also linear, quadratic, and so on, any polynomial Poisson brackets. But what we want, first of all, we want to define the Poisson brackets on the vector space of traces, just as before. But now the reasonable question is, what are traces for elements of free associative algebras? And the answer more or less known for expert in representations, but it doesn't matter. This is the definition of the trace vector space. We need to consider the quotient space over a commutator. Commutator is not commutator in the sense of algebras. This is a vector space generated by all commutators. It's a linear space, and the quotient space is also linear space. We have no any multiplication here, so we have no any Leibniz rule. Okay, so they will be, I would say, functions in our situation. But to define the reasonable class of algebras, we need the left and right multiplication operators. LA is multiplication operator by A, and RA is. And we consider the associative algebra generated by all these operators. It's the first glance is not trivial idea, but if you try to understand in the matrix case who are Hamiltonian operators, who are recursion operators, who are Fréchet derivative operator, and so on, you will see that in contrast to the scalar case, it will be operators of left and right multiplications, no elements from the algebra itself. But it's reasonable. And now we want to use our free associative algebra A and also associative algebra generated by all left and right multiplication operators. And now this is the definition. Let's look to the definition. What is unclear? I would say, first of all, these brackets are usual scalar brackets, and gradients are vectors. And this is a matrix. So it looks like usual standard Poisson brackets, but gradient is not gradient, and this is not a matrix. And now I need to define the concept of gradient and explain who are these matrices. But the letter is simple. They are elements of this tensor product, or simply they are matrices whose elements are our local operators. It's some matrix with left and right multiplications as entrances. But about gradients, we will discuss it. And
Volodya, this definition was in our paper 2000, right?
What?
This definition was in our paper published in 2000.
Yes, this approach was developed in our paper published in 2000, and especially this class of brackets with such, sometimes people call this Poisson tensor in the scalar situation, sometimes Hamiltonian operator, but the class of Hamiltonian operator, we call this local. It was introduced in our paper with Sasha. And this is the main identities. This means that this sum is not zero, but it's equivalent to zero up to vector space of commutator. This is zero. This belongs to the commutator A with A. So it's because our Hamiltonians, our F and J belongs to the commutator vector space, this means that it belongs to this space.
No, I would say, Volodya, I would say that your Hamiltonians or our Hamiltonians belong to the quotient space of A over this commutator.
Yes.
And the Poisson brackets also belong to the quotient space. So that is a zero in the quotient space.
Yeah, exactly. By definition, this vector space is quotient space of A by the commutators, a linear vector space of commutators. But now about gradients. The gradient of some polynomial, we defined the gradient of polynomials from our free associative algebra, but actually this is a well-defined object also here. But let's start from the situation where H is a non-commutative polynomial. It's an element of free associative algebras. So this is a vector, and how to define the components of this vector? We take, it looks similar to usual definition, but up to one. So we consider additional non-commutative elements. They are not elements of our free associative algebra. If we want to define them, we need to consider some double, but let's simply substitute instead of xk plus epsilon delta k. Delta is also non-commutative. And now we differentiate this with respect to epsilon. Epsilon is usual parameter, number, complex parameter, differentiate, and substitute epsilon to 0. What we will have here, I have an example. Maybe it's simpler to follow an example. This is h. Now I want to define the gradient with respect to u. So I substitute instead of u these guys, differentiate, or if you want to find linear part of превращение, я не знаю, как по-английски. But you immediately, in the polynomial case, you consider the coefficients at epsilon. Is the coefficients of epsilon, and you will have this delta 1 in a different places, of course. But to define the gradient, you need to move this delta to the left.
You have a misprint. In your Hamiltonian should be UV, UV, not UU.
Yes, UV, UV. Sorry. But how can I do this? In the space of traces, we can use the permutation of monomial, because this is the same as, say, send the monomial from the generator from here to here, or subtract some commutator. Up to commutators, the monomial related to permutations are equivalent. And in this case, to get delta 1 on the left, I need to send this to here. It's okay. And about this, I send this to here. So this means that this is equivalent up to commutator, the following expression. And by definition, this is the gradient of h with respect to u. And the same, about the gradient with respect to v. We need to do the same calculation to get both gradients. This is can be written in this form, and the second part of gradient is given by this. So now it's more or less clear. We have this delta in different places, but we need to send delta to the left by the subtraction of commutators, or the same by the cyclic permutations in monomials. And it's easy to verify that if f is commutator or linear combination of commutators, then gradients is 0. This means that this definition is correct not only for h belonging to A, but also for h from our quotient space. So the gradients give me some vector with the components. The components of gradients are elements of associative algebra, by the way. And this formula does not depend on representative of class from from tau. Now, usually the Maxim Kontsevich used this notation for gradients, and he calls it non-abelian partial derivative, but this is not derivative. This is not a vector field, and this is just gradient I defined, and this is simply for simplicity.
Volodya, I'm sorry, I missed. To my opinion, the gradient has values in the space of traces, not
No,
in the algebra.
no.
Uh-huh.
Look, we move this to the left, and here we have an element from non-associative algebra. It's rigid. If I send it to left, this is uniquely defined element of free algebra.
Yes, but all these manipulations are defined up to a commutator.
No, H is defined up to commutator, but the gradient is well defined because the gradient of commutator is 0. It's well defined if you want to the quotient space, and also well defined on the associative algebras.
Okay, I should verify. Thank you.
And now the
But
important.
Volodya, in your
Yeah.
example, it's quite funny that the gradient lives in the result is commutators, you know, can be written in commutators, which is not always the case.
Sorry?
In your example, your gradient, look, both elements are commutators,
Yeah.
which is not always the case. You know, this is it.
No, it's
This
not
particular,
always the case. There are some polynomials.
yeah, the
from
sample
associative algebra. It's
right,
by
confusing.
occasion.
By occasion, yeah.
Now, the statement from the Kontsevich paper, Rubtsov told me that somebody obtained this fact before. I don't remember who, but I'm not expert in references. But it turns out that if you take any polynomial from A, find the gradients, and they are components of gradients, then this expression is identically 0. This is the identity in A. This belongs A, the commutator of gradients with the generators and the sum. Okay, let's fix this fact, and it's important for us in future. Now, what about the evolution of Hamiltonian equations on non-associative, free associative algebra? Of course, this given by the standard formula, the gradient is defined. Theta is the matrix with entrances belongs to right and left multiplications. But what does it mean? Of course, this means that we consider derivation of free associative algebra. This formula will give me a derivation of A. The right-hand side belongs to, the vector belongs to A, and here also. So it's an equation in A. But what is interesting for me, Sasha, I never thought about this, but suppose we have the Poisson brackets defined by the Hamiltonian operator theta. Suppose we have two Hamiltonians, and I consider two corresponding derivation. Is it true or not? We know this basic fact in the classical Poisson brackets theory. the commutator of the vector fields here correspond to the vector field corresponding to the Poisson brackets between the Hamiltonians. It seems to me that this is not correct for some non-Abelian brackets. I'm not sure, but I cannot prove this in this setup. And also, there is a paper by Artamonov who discussed this story, but he introduced a lot of names, Lade brackets, double Poisson brackets, blah, 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 and it was difficult to catch the essence. But if I understood him properly, by the way, he considered such brackets in general. I mean, when we worked with Sasha Mikhailov, we consider only this class of brackets with local, how we say this, Hamiltonian operators. And he considered any brackets who satisfy to these identities. And he additionally assumed this property, and he obtained some different structures. And I don't know whether if we additionally assume this, we will have some additional information about theta or not. It would be nice if some young guy to play with this question. But it was unexpected for me, Sasha. Now about...
Well, I think what can be proven, I mean, just I was thinking about this as well, that this bracket between H1 and H2, what you can show, if the flows commute, then this bracket belongs to the center of your algebra.
What if the vector fields commute, the brackets is not zero, but belongs to the center?
Well,
yeah?
could belong to the center of the algebra, yeah.
Maybe, but if they are not commute, simply the relation between commutator and brackets. If they commute, maybe. But what about the general two Hamiltonian flows? Okay, now I want to get some relations between the first part of my talk and with the second. In the terms of the Hamiltonian operator, for example, our linear non-Abelian Poisson brackets correspond to the case when the entries of this is linear in operator of left and right multiplication. This is a general formula. It follows from skew symmetricity. So in this case, we also have the set of B, K, I, J. And it's easy to verify that the non-Abelian Poisson brackets is really bracket if this is the structure constants of associative algebra. In this case, no relation, some problems. And we have problems here. This is a general ansatz for quadratic non-Abelian Poisson brackets, quadratic relations between left and right multiplications. It follows from the skew symmetricity. And the statement is, if A and R satisfy to this set, then we have real Poisson brackets in the non-Abelian sense. So any brackets of trace brackets on the matrices produce me Poisson brackets on free associative algebra. It's more or less evident because in our trace brackets, by definition, the commutator of traces is trace, and we replace these traces of matrices by the elements of quotient space. The computation is very simple to verify that if we have a trace Poisson brackets, then we have a non-abelian Poisson brackets. But what about the opposite direction? Suppose we have a non-abelian Poisson brackets, so we need to prolong these brackets to the matrix elements. The situation is the following: we know the brackets between traces, and we want to know, is it possible to get the brackets on all matrices entrances such that for traces it will be just initial. It's a reasonable question, and as far as I understand, the answer is no. Not for any non-abelian Poisson brackets we can prolong this, extend this to the all matrix entrances for some trace bracket. And
a question. Well, maybe it's a silly question, but you have your brackets on free algebra, so you can consider a representation of your free algebra by matrices.
Yes.
And the representation of all your structure, carry all this representation to all your structure. And whether you will get your trace brackets on matrices then.
Yes. But I know only the brackets between traces in the matrix representation. And I want to reconstruct the brackets between elements, between entrances. I don't know the brackets between entrances, right? And the question is always possible to extend these brackets between traces to the matrix entrances?
In my view, this is not really required, because what you need basically the structure of Poisson algebra. Well, you have your traces, and you need action. You have your Hamiltonian derivation already, and you have a bracket between traces, and that's what we really need. And the rest,
it depends on what we really need. But I want to discuss the relations between trace brackets on the matrices. For me, this is more reasonable object. And non-abelian Poisson brackets, no one-to-one correspondence. We have some non-abelian brackets which cannot be extended to the representations, to the entrances of matrices.
okay.
And I am sure that it's correct, but I have no any example. Why? The problem is, suppose I have, say, quadratic non-abelian Poisson brackets, and I want to lift it to the elements of matrices. If I could prove that this extent is also quadratic Poisson brackets for elements, no problems to construct the examples. But who knows? Maybe the Poisson brackets between entrances are rational, for example, and only for restriction to traces, it will give you a polynomial relations. I would be happy to see the example but I'm sure that the definitions are not equivalent. But there is a standard way to define the Poisson bracket between entries. If you want to use the usual trace form, we can represent they in terms of trace, but not only elements of non-associative algebra, but also matrix units. And if I do this, and if I postulate this formula, I will have immediately some brackets on the elements. And that's the way we usually obtain the brackets on the representations. But unfortunately, this way is not universal. Sometimes these brackets on the entrances not satisfy to Jacobi identity. We had Jacobi identity for non-abelian Poisson brackets in the defined sense, but after this natural lift to matrix elements, we lose the Jacobi identity. Okay, now I think the time is over. Or what is the regulation? How?
Well, traditionally we have 1 hour of our seminar, but the subject is so interesting, so we can prolong.
Actually, you asked me to
Yes.
to say about this, but the introduction was, let's try to go. I will skip some details, but what is the situation in the classical scalar situation? The coordinates on the fine space, and this is the Poisson brackets, Pij, some polynomials. The question is when we can descant these brackets to the projective space. What does it mean? It means that I want to define the bracket space, this bracket on the space of homogeneous functions, only homogeneous functions. Is it possible to restrict the brackets to homogeneous functions such that the Poisson bracket is also homogeneous? It's very easy to verify that it's possible only for quadratic Poisson brackets, because the homogeneous functions are functions which invariant with respect to scaling, and this Poisson brackets is unique Poisson brackets equivalent with respect to scaling. So this means that we can restrict this to invariance of the scaling one parametric group, and the result is more or less evident. We consider some generators of homogeneous arguments of homogeneous functions, and between these guys, our quadratic Poisson brackets between cubic. And also we have some linear terms here. It becomes not homogeneous, but the number of u is now n-1. For example, this is a simple example of so-called elliptic or Sklyanin brackets. It's quadratic homogeneous, but if we go to the ratios x1 over x3 and x2 over x3, the brackets between them becomes not homogeneous and cubic. But what is the, let's skip this. also this. And also, this is a very important point here. Suppose we made this restriction. We had brackets in the affine space, and now we have the corresponding brackets on the projective space. We went to the ratios. And suppose we want that for homogeneous functions, this is real Poisson brackets. The question is, what about the Jacobi identity for the affine Poisson brackets? Again, we have these brackets and we don't know about Jacobi identity here. We make the reduction and we have this bracket, and we know that here we have the Jacobi identity. The question is, it's necessary that here we also had a Poisson brackets or not? Is it possible to get the Poisson brackets here from non-Poisson brackets here? It turns out that the answer is yes. Why? Because we need only the Poisson brackets between homogeneous functions, and any homogeneous functions satisfy to Euler identity.
Sorry, homogeneous of what degree?
Of any degree. I mean, all xi has the same degree, homogeneity in the school sense.
I mean, if I take, I've been taught that Euler field has the property that when you apply it to a function of homogeneity n, it gives you n times f, not 0.
Yes, but we consider the pure homogeneous function. This means that they are functions of these arguments.
Of homogeneity 0.
Yes, of homogeneity 0.
Okay.
Homogeneous means homogeneity 0.
That was my question. Okay.
Yeah,
Now I see.
Thank you. So, and what does it mean? This means that this means that this identity for homogeneous functions must be not 0 identically, but 0 up to this relation. So I feel that this is so. If for this Poisson brackets, the Jacobi identity is not identically 0, but 0 modulo Euler relation, then after the reduction, it will have the real Jacobi identity. That's what I want to say. And this is a highly non-trivial question. Okay, suppose we have this construction, and it can be obtained not from one quadratic homogeneous Poisson brackets here. It turns out that we can obtain this from non-Poisson brackets, but always there exists a Poisson brackets quadratic such that it follows from the quadratic. It's I don't know how to prove this. It's more or less no. But what I want to say is that in non-abelian case, this is not true. And what is By the way, Sasha, this is another way to write the Poisson, non-abelian Poisson brackets of our type, where our Hamiltonian operator theta is inside of this. If you don't want to use this form, you can play with this, but of course, this partial derivative are not partial derivative, but gradients. The same story about the reduction of quadratic Poisson brackets, non-abelian, to the polynomials on such ratios. Now the order of them are essential, and but it's easy to verify that for non-abelian quadratic Poisson brackets, this reduction is also possible, and we will have the following restriction. And now the brackets will be degree of 4, not 3. In the scalar case, all these terms cancel out, but in general, there is possible reductions to non-commutative projective space. For example, if we want to generalize this Poisson brackets to non-abelian case, there is a following formula. And in the commutative case, this bracket coincides with above. The story was, I tried to find the non-commutative generalization of the Sklyanin, simple Sklyanin brackets very intensively, but the result was negative. No non-commutative quadratic Poisson brackets which satisfy the Jacobi identity. This is the best what I found. In the commutative case, it goes to the proper brackets, but the brackets does not satisfy to Jacobi identity.
What is the defect of that? So if you compute Jacobi identity, what you will have on the right-hand side? Modulo what? It satisfies probably modulo something.
I will say up to the Euler relation, we have Euler relation here also, and up to the Kontsevich relation. In the scalar case, we have this.
But Kontseviches look like Euler because commutator is differentiation.
Yeah, but from the different place. We have now two. Euler have it here, and from Kontsevich we have also the same, but with the generators from the right. And up to these two identities, it's okay. And what does it mean? It means that if we consider the restriction of this bracket to a to the projective space, we will have the Jacobi identity. So on the level of scalar situation, we know how to generalize these brackets, but don't know how to generalize this. It's two different problems. And when we understood this, that here we need to find the brackets which are not Jacobi, have no Jacobi identity, but have Jacobi identity modulo Kontsevich and Euler relations. Then we, by projection, immediately obtain a non-homogeneous non-abelian brackets here. And we found all such formulas for all elliptic Poisson brackets to find the analog of non-homogeneous elliptic brackets on the projective space. So actually, this is non-abelian brackets on the projective space for that. So this is not satisfied to Jacobi identity, but this satisfied. It was obtained by projection to the homogeneous functions. And this is two identities. This is Euler, and this is consequence from Euler and Kontsevich relation. And this is the answer, but to give some explanation, we need to define some theta functions and theta constants, because in the scalar case, the coefficients in the elliptic brackets can be defined in terms of theta constants. For small n, instead of theta constants, we can write sometimes radicals, but for general n, these elliptic brackets are not, how to say, it's difficult to work with them. For example, to verify that these elliptic brackets satisfy to the Jacobi identity, you need to play with non-trivial identities for theta constants. You need to know how to work with the theta constants to verify that the brackets is really Poisson brackets. So this is more or less all what I want to say today.
Volodya, thank you very much. Are there any questions?
Well, I have probably not a question, but a little comments, because it looks, I first time see on this picture, but it looks that your conditions, which you have on the right, I mean, these two conditions, yes, 33. I really want to see how is it really proportional to these elements, because these conditions looks like a linear subspace in your space of homogeneous functions. Yeah.
But actually, you need an ideal generated by these two.
Ideal or a linear subspace.
Ideal. You can multiply. So the Jacobi identity must be up to ideal, double side ideal generated by these two
double side ideal.
elements.
Double side ideal, right? Because some time ago we discussed with Victor Buchstaber a kind of generalization of these anti-Frobenius algebras. That what was my question, where your form takes value, and in this generalization, the form takes value in a linear space, and since there are examples, etc., from commutative and non-commutative world. That is why was my question. Probably what you're doing, you consider not maybe your form and your Frobenius structure will be anti-Frobenius, will be just this, how we call cyclic Frobenius algebra.
But in my exposition, there is one-to-one correspondence between associative Young-Baxter and such Frobenius algebras. But if you consider your Frobenius algebras, what is the analog of associative Young-Baxter? Do we have still?
I don't know yet. I don't know. Maybe we can talk about later.
Okay, I have me too. I have a question about the problem of reconstruction. So you, in this non-commutative approach, you can regularly construct the structure on traces, and there is a problem of reconstruction of these structures on other, for example, matrix elements.
One of the problem, yes.
The problem. Could it be specialized in, for example, in universal enveloping algebra of SLN? Is there some ramification, some simplification of the problem in Yangians?
I never thought about this, but probably it's a very good question. It would be nice to discuss this.
Okay.
May I also ask a question? I didn't quite understand if you were talking only about free algebras or not. I mean, if there is if not, then I'm sorry if you have been talking only about free, and the question is, what is known about non-free algebras? Because actually, this trace space for algebra, A modular the commutators, is closely related to various things like cyclic homology and everything. So I just wonder whether something is known for non-free algebras.
This is a reasonable question, but unfortunately, I am working only with free associative algebra, and about arbitrary algebras, probably the best references this, number 3.
I mean, Crowley-Bovey.
Yeah. They
Okay.
develop a general approach without any free associative. And also there is some relation between the Poisson brackets and double Poisson brackets, but I don't want to discuss it here.
Yeah, maybe next time. Okay. Actually, I would love to invite you to our seminar, but we'll discuss this step separately. Okay. And also it's interesting to the relation with cyclic homology, but it's also another question again.
Oh, can I ask also? Thank you for interesting talk. I have the next question. I remember that Kontsevich, in fact, considered not free associative algebra. He considered group algebra of free group. Yes, and try to construct Poisson brackets. And I have the next questions. Is it possible to extend your Poisson bracket from free associative algebra to group algebra of free group? First questions. And the second one, do you know the result about construction of Poisson bracket on group algebra of free group, maybe on some other group, free nilpotent, free solvable, and so on?
Also very interesting questions, but also I cannot say any informative.
Okay. Thank you.
But in a sense, you have inverse elements, because when you consider something -1, so that's very close to, it's not for algebra already.
Of course, we can consider some Laurent, non-commutative Laurent polynomials. No problems to generalize this to this case.
Laurent, you consider
I mean, if
Laurent polynomial with commutative or with
non-commutative.
Non-commutative. Laurent commutative. Okay.
That is free group.
And in this case, is it isomorphic to group algebra of free group or not? Do you consider what does mean Laurent? I think that way are isomorphic, yes? See, you consider the monomial, the powers of x, product of powers, with some coefficients and take the sum. And now we consider not only positive powers, but we can take negative powers.
Yes, no
And
problem.
this is, you say that it's possible to construct Poisson brackets on this object.
No problems to define.
No problem. Okay, thank you, thank you.
Okay, if there are no other questions, I'd like to thank you once again. And we stop now. I wish the next talk will be also interesting.
Thank you.
Is it
But
published, Volodya?
I'm ready to discuss any points from here. I understand that there are a lot of interesting unsolved problems here. Maybe solved, but simply I don't know the results. But it looks interesting for me.
Теперь только русскоязычный, можно по-русски говорить.
Ну хорошо.
Володя, у тебя это опубликовано?
Что именно?
Ну вот то, что ты сегодня рассказывал.
Ну вот тот кусок.